I didn't feel that I had done Scala. Scala's two aspects of Scala justice in my presentation last time. So I went pretty quick over this matches and match expressions, which are some of the most interesting aspects of Scala's support. And then also I didn't hit on traits well, and those are also a fairly interesting component of aspects. So I talked about match expressions at a very high level last time. So the syntax here is a little bit like the if expression syntax in Scala, in the sense that you have some criteria where you are selecting different outcomes based on an expression, and it evaluates to a value. But they provide something quite similar in its most primitive form to switches in C and Java and other C-like languages, C++. So with switch, you don't have just two outcomes like if, but you instead have many outcomes. But to compare them to switch is to really not do matches justice, and we'll see why this is. A match expression will list a bunch of cases, and they will execute from top to bottom until one of them succeeds. It's very important to understand. But a key nice feature that we'll be concentrating on is that they can take apart the thing that's being matched. So when it matches, you have all the information you need to operate on it. And it can take apart the pieces you need to work with to then handle it. Okay? And so I call it decomposing, or what was the term I used for it last day? Deconstructing. But the term that's often used in the Scala literature is destructuring. So you basically have something that you're handling. You say, I've got one of these. And it automatically sort of binds certain variables that tell you about that thing that you've matched up. And that allows you to sort of handle that. And we'll see how case classes factor into that, but how you can use unapply as well. And this unapply is going to say, hey, is this a match? And here's the information you need to operate on it, if so. Okay? Okay, so we're going to see a bunch of examples with this. So the most trivial case that I talked about last time, and this has one bug here. There should be a arrow like that. Is this? So here we have some expression. We say, hey, what's the value of this expression? Is it 1? Is it 2? Is it 3? Is it some other integer called n? Or is it something else? This is default, the default case, underbar, okay? The default case. Here, there's a value, and we refer to it as underbar. We're not going to need to refer to it, so we just handle the default case. You don't have to have the default case, but in general, it's good practice. You want to know, hey, did I forget about some possibility as a developer, even if just to put an assertion false here. Got all handled. That's a good practice for defensive programming. Put in an assertion failed if you handle the default. If you think these are the only possibilities, there's no way it could be this, put it in there, catch it. And if it blows up sometime, you know, hey, I wasn't counting on that. I forgot to extend this when I extended this other part of the program. Okay, so this is the most simple case. Even this is a step above switch, because you can handle, well, a couple things. First of all, there's no fall through here. There's no, if you hit 1, you fall through to 2 unless you do a break. None of that nonsense, okay? There's a study done of switch statements in C and Java. And what they found is, I think it was actually C, maybe C++. And what they found is something like 97% of the time in switch statements where something fell through, it was unintended to do it. They forgot to put a break. Bad things. So that's one way which is better. But another way is it has this syntax where you can get a value. So this handles a whole bunch of values. Which values does it handle? The ones not handled above it. So this is not going to be handled, this case n being integer. That's not going to be handled, ladies and gentlemen, for this case where n equals 1. After all, that would have been handled up here. 2, 3, maybe this goes down to 10, and then this is handling everything above 10, okay? And the nice thing is we have n now, and we can do things with it. We know what value it is. Okay, so that's kind of a nice feature here. Okay, here's another one. So here we have matches going on, and we have this guard syntax, ladies and gentlemen. This guard syntax where we basically say, okay, look, case n, if n is prime, then we'll do this. And so then we can refer to n over here. If n is prime, it'll fire off this handler, and n will be checked, is it prime, okay? Here, n, if it's square, we know we have a square in this handler. We know we have a value that's a perfect square or something. And then here's the default case. So you can put in these guard statements. And actually, I meant to double check. I don't think you can do this. I think the underbar here you can't use in this sort of way that it's bound here. I'd have to double check that. I meant to check that. In any case, case underbar is the default case, it falls through. So these are guards, and these basically say, hey, handle this only under these conditions. And as you might expect, the guards can be really useful for handling criteria. Let's check out some more possibilities here. Okay, expression like this, in contrast to switch, can be used for things that are objects, not just for primitive values. So you can have switches on strings, you can have switches on hash tables, you can have switches on primitive values, any of these, right? So in this case, we might have one of many different object types. Maybe this is an object, rather than, in other words, its parent type is object. We don't know what type it is. And we're asking, okay, if this is a string, then we'll handle it like this. If this is a double, we'll handle it as a double. If this is a char, we'll handle it as a char. You'll notice that, again, we bind this value. So this one, this code over here can refer to D and know with confidence, hey, this is a double, right? This is a double version of this, which is useful. We can also have sort of general matches, but restrict the type. So this case here, the second to last one, will handle cases of all bytes. It's not going to refer to the value over here on the right. It didn't bind it to a value, but it only handles bytes. Whereas this bottom one handles all cases. Okay? So we can put in these type restrictions, and those will also be matched. Those will be criteria that need to be matched. Now, a word about this. Object-oriented purists might think poorly of this. And one of the reasons is, if you have access to the different things being matched here, generally you don't want to handle them in this sort of statement. You want to have a polymorphic method. So if these are different types that you've written, if they're types that you've written, each of those types could support a method that does the appropriate thing. Instead of switching on what type it is and then doing the thing, you just call this method, and thing of type A knows to do this, a thing of type B knows to do that, a thing of type C knows to do that. All you do is you call the appropriate method. So just a caution in the object-oriented sphere, doing matches like this with types that you control might be better replaced by polymorphism and dispatching off of values. So the idea here is we have a superclass, and we might have underneath it several subclasses here, B, C, D, and we provide for this guy a method, perform task here, and this is perhaps not even defined here. It's just an abstract method, and then each of these defines it. And instead of switching off whether they're an A, B, C, or D, or whether they're B, C, or D, and doing the appropriate task for that, perform task, each of these defines it. Each of these defines it, and then we just call it. We just call perform task on our A thing that's apparently A, and it calls off to the appropriate method here, right? So that would be a cleaner way to do things if we control these types. But sometimes we don't control these types. We didn't write string. We didn't write double. We didn't write char. But we want to be able to handle them. So this type of match can be very useful for that. Okay? Now, this is where it gets really interesting. Okay, you know, type restrictions, naming, not falling through. Those are all nice things. But where matches really come into their own is in this sort of context, where we have things being matched that are composite in some sense. So they're made up of pieces. And when we do the match, we can extract those pieces and do things with them, okay? So this is a big num. And it turns out if you do big num slash %, you get a, with some value, you get a pair, which is a quotient and a remainder. So just to be clear about this, if we had an int and we called it, by extension, I in Java or C or C++, and we had some I %n, what is this doing? It is computing the what? It's the remainder, and we write it as mod. It's the modulo operator, modulo. And this is kind of a generalization of it. It not only returns the remainder, it returns the quotient. In other words, it returns this divided by that. So if we do this slash %, it returns not just the remainder, but a quotient. It returns it. Hey, what is this in Scala? You tell me. You saw it last time. What does it mean if I have it in parens like that? It's begins with a T. Yeah, it's a tuple. Tuple, tuple, however we pronounce it, it's a pair in this case, right? Okay, and in general, Scala will support, general tuples or tuples up to about size 22. Okay, here, ladies and gentlemen, you have cases. And so here, we're matching this tuple by possibilities. So here we have a quotient, and we have 0 as the second element. And here it goes into it exactly. Here we have case 0, remainder. Okay, so in this case, it goes exactly in because the remainder is 0. So we handle that. And we know what the quotient is. We've named it. And so we can use quotient over there. Here, it goes in 0 times and there's some remainder, and we can refer to the remainder over here because the value has been bound. In general, we'll have a quotient and remainder, and we handle the general case, but we know these cases have been ruled out because we've gotten down to this. So here we've taken this tuple and we destructured it into these pieces that are given names and which can be referred to over there. But not only that, we match them according to the features of the situation. So here we're restricting it to cases where the latter is 0. So not only are we naming things, we're sort of pattern matching almost the cases, right? Right? Does that make sense? Okay. Pretty sweet in my mind to be able to do that, to handle these cases. Now, I mentioned last time that Scala has an option value, and it turns out this is very similar to optional. And in this room, 2 weeks ago, I presented something on monads, and monads were an advanced concept, but they're a concept of significance. And I talked about optional because it's hard to talk about Java 8 without doing some justice to optional and to monads, because they're pretty key for understanding certain of its operations. And frankly, in your lives as programmers, you'll probably see this more and more. So what is an optional? Can anyone remember? What's an optional? If I have an optional int, what is that?
It may be an int or it may be nothing at all.
It may be an int or maybe nothing at all. So where might I get nothing at all? Like, what sort of thing might result in nothing at all?
Square root function?
Yeah, square root. I love it. I love it. So I take a square root of a negative value and I get back nothing at all, right? So maybe that would yield an optional double, right? So either it's a legit double, 0 or higher, or you know, for the values given to square root of 0 or higher, or it's a bad value, and maybe the thing returned is 0 or higher, or it's nothing at all, right? So you take a square root of a negative number, you get nothing back. How about another case? Where could I get a case where I get nothing involving streams? So maybe I try to reduce the stream, that is, by reduce, I mean like sum it up. If it is empty, and I didn't specify seed value, I might get something that's nothing, right? No, there's no particular value. No value. I get back, right? Okay, ladies and gentlemen, so these optionals, they handle these cases where it's something of the type T, or it's nothing at all. There's nothing there, right? It's empty. And I argued that monads are kind of like wrappers or like a package around this thing, and it keeps track of what it is. Well, it turns out we can handle this with match statements in a pretty sweet way, in the sense that we could say, hey, if it's something, something with value v, and then you just use v. Now, v is not an optional; it's the actual thing in it. It's the number that you got back from square root if it returned a number. Otherwise, match null. But generally, you don't want to do this because there's a thing that's equivalent to this, essentially, or that handles most of these cases, which is get or else. So here you have an optional, and you say, hey, get me the value of it, or if it's empty, use this value instead. So I'll use 0 or what have you. But occasionally this may be useful. So we can do this, and this is an example of destructuring. I'm extracting, I'm sucking out of it the value v, and I suck it out and I use it there, right? It code using v, just like that. Unfortunately, Scala doesn't have those side effects. It does sound effects built in. Okay, so here's an array case. Okay, so we have an array, and we call off to some function. We get back an array. Okay. Now here we're doing a match on the array, and you tell me. I'm gonna stand in front of this as I am wont. What cases are being handled? What is this first one handling, do you think? It's handling a case where the array is what? Empty. How about this one?
The value 0?
Yeah, it's an array and it contains just the value 0. How about this one?
Any values? Or?
Yeah, but of single length. So it has a single value, and we call that v, and then we can use v here, right? We can use v. How about this guy here? What length of it is it? Length 2,
with 0.
and it just has zeros. This case, given that it's below this one, this is what?
0 to any length?
Yeah. Well, actually, the first one is 0. The next one is, we know it's not 0. It would have matched this guy here. So it's some non-zero second value. How about x and y then? Given that they're below all these others, and you note the importance of context here. Given that it's below all these others, what is this handling?
2 non-zero values? Yeah,
so the array is of length 2, but we know that both of them are non-zero. Nice way to put it, yeah. And then, what is this one down here? Case 0 array if 0 array dot for all this thing. What is this thing here in Scala? This is it's one of my favorite things. If you recorded my word cloud in this room, it would probably be like the single biggest element. What is this thing?
Anonymous function.
It's an anonymous function, yeah, it's a function. Or closure, as it were, but it's a function in this case. It doesn't have to remember any specific extra information. So this is a function, and what is the job of this function in life? What is it doing? It's taking a value v and doing what with it? It's seeing if v is 0, right? So what do you think this thing does? If 0 array dot for all this,
Checking if the array is 0?
Yeah, check if the entire array is 0. In that case, we'll handle it here. how would I refer in here to the array? What would I use as my name for the array? I could use 0 array, right? I could actually use this array up here, but it's not as nice. It's more coupling different parts of code, because now maybe someone renames this. Maybe they place an Osgoodian name in it, and it becomes much larger up here, and suddenly the code down here would break if you're referring directly to array. So instead you refer to 0 array. 0 array has been bound by this, and so it's less subject to sort of change out from under you. So I'd refer to it as 0 array, and it makes it clearer, right? It's a 0 array. Okay. Great. And here's the default case. So here's destructuring an array. Okay. Now, one thing I didn't show here, which I will show now, would be this case. And this is pretty sweet. Would be this case. If I have, for example, hey, come on, get back there. Would be this case. There's a syntax here that can be quite nice, where you have something like this: 0 followed by anything, however many times. Handles case of array, starting of array of length greater than 2, starting with 0. Okay. Now you folks may not be able to see that, so let me put it up on the big screen. So there you go. So this is basically saying an array of starts with 0 and then has any length. And I know it's greater than 2 because I handled the 2 case up here. Okay, the case where it's of length 2. Okay, so here we are having an array of any length, and I can handle it there, but I might want to give it a nice name too. Okay, destructuring an array. We're taking an array. Destructuring basically takes something. Here it's an array. Here it was an optional value. Here it was a tuple, and it takes it apart, and it handles the pieces in a nice named way. Were that only possible in Java? Were that only possible in C++? It's sweet. Okay, here's another one. This is from a book I strongly recommend, Kay Horstman, who some of you may know from authoring the Big Book of Java. He also is author of Scala for the Impatient. It's a great book. It's a really nice book. And I'd recommend it strongly. He's also the author of Java 8 for the really impatient. I would also recommend that book. Okay. Anyway, here is matching a list. Okay, so we have a list, and we're matching different cases on this list. Now, one thing I want to highlight here is this operator : Does anyone remember what that operator means in Scala?
Well, is that a range?
So, no, it turns out it's not a range. Good guess. Turns out it's a list construction operator. So we sort of put this is the head and this is the remainder of the list. In many ways, it's like cons in Racket, or probably you folks are innocent of Common Lisp, but in Common Lisp as well, cons. Any case, I would note that there's a similar operator for streams. Does anyone remember what it is? It's actually hash : and basically it allows you to not evaluate the thing after this. So you could specify a complex expression here that might, that will compute the rest of the stream, and it won't actually compute it. It'll get it ready for computation when you need it, because lists are lazy. Remember that? Yeah. Okay. So this is list construction. So what is this doing? What is this guy handling? A list of length 1, which starts with 0. Okay. How about this guy further down here? The last one above the default. What is he handling, or she? What is this family? Is this a blank 1? It starts with 0, but is it a blank 1? Not necessarily. It's followed by tail, and tail could be a big list, right? It could be a mammoth list. We know it's not nil because it would have matched this first one, so it's not nil. But now we have tail bound, and we can use it in this expression over here on the right if we wanted to. Notice this arrow type operator, which is saying, for this case, do this. Okay, how about this guy here, or this gal? Case X, Y, nil. What is it matching? Length, any less the blank do, and then we extract the appropriate things. These are the first two elements of list, right? May seem a little bit puzzling, but think about comparing this to the code that would otherwise be required. If this thing go and you get the first element of it and you append it to the second element of it with get expressions, this might be a little bit off-putting at first, but it's much more succinct. It enjoys the virtue of concision. It's sweet and expressive, whereas if you had that if statement and so on, and a bunch of ifs, if else, if else, if else, it would kind of blow up this code. And you wouldn't have this nice kind of naming. While you're testing it, you name it. That's the beauty of it, right? While you're testing if this is true, you're also naming it, and you can just use it. You don't have to introduce things to then subsequently extract it. If this is true, then extract it. The extraction occurs when you're testing if it's true, which I think, I don't know about folks in your generation, but I personally think it's sweet. Okay? Okay, we saw this last time, and I want to explain this better. So here we have this function twice. Ladies and gentlemen, twice. And this object twice, okay? And it has a function apply, and it has a function unapply. Now, I want to highlight something with this that I didn't emphasize last time. Apply for an object, it's actually really nice. Believe me, it's really nice. If you have apply in an object, this is a companion object in Scala. If you have apply here, what that allows you to do is to use the name of the object and apply it to a value. In this case, the value would be x. And so you could write twice, some integer, right? You could write twice of 3, or you could write twice of minus 1, what have you. That's what apply allows you to do. We talk about apply. You apply a function, so you can apply twice, as if it's a function. So you don't have to say new of it, you just apply it. Now, if you have apply in a class, ladies and gentlemen, if you have apply in a class, that allows you to take instances of the class and apply them as if they're functions. So if we had a class, C, and it had an apply operator in it here, and it took in, just to make it comparable, it took in an int here, just like this one did here. And suppose it returns an int. Okay, if we had this in a class C, then we could create a new instance of it, new of C and whatever constructor arguments, and then we could call it as if it were a function. We could pass it -1 or whatever. So by virtue of putting an apply in a class, we can call instances of the class as if they are functions. Okay? If we put it in a companion object, if we put it in an object, then we can call that thing as if it's function twice. Okay, so that's what apply does, and that's why we could say twice of 21 here. Okay, unapply is going to do something different. Unapply job in life is particularly to deal with match expressions. And its job is going to be to basically handle the case with this case of this thing. And what it's going to do is it's going to here take a value that's being matched, and it's going to see if the value matches some criteria. And if so, it will return true, if it doesn't have to get a value. But otherwise, it will return the value, ladies and gentlemen, that it matches up. So here, it returns sum of z divided by 2, okay? So here, what's happening is twice is getting a value given to it. And here, we are going to be testing, okay, is this value, excuse me, I misspoke here. So this value that it's testing, z divided by 2, that is the value that's actually being matched here. That's x, okay? So x is being matched, unapply is taking in the value being matched, and it's testing, is this value even? Is this value twice something else, in other words? And if so, it's going to return a sum here, in other words, an option, that has the value z over 2. And that's going to be bound to n, okay? That's going to be bound to n. So the value that unapply operates on is the thing being matched. The value that is shown as n here, the value that's sort of being, or the expression that's being used to with n twice, the name of the value, that's going to be bound to this thing returned. If unapply returns none, it didn't match, in which case we'll go on to the next case. But if it returns some, that has the value that we match to n. And how would you handle a case where it needs to match several things? Like it has an m and an n. What would you return here instead of sum of z over 2? What would you return? Well, you return a tuple. Okay, return a tuple of two things. Okay, it would be a sum of a tuple. So that would allow you to return two things, m and n, for example, bind m and n. So this n, in this expression, case twice of n, that is being bound to the value within the sum if there is a value there. If that sum is, if the option value being returned is empty, then it just goes on to the next case, okay? So unapply allows you to handle this kind of matching in a way that you can specify what values are bound when you call unapply. In this case, it's just one value. It can handle many values. And those are handled through an option. If the option is none, if it's empty, the return value, it didn't match. If it has some value, then those values are used to bind any variables here, which can then be used over here on the right-hand side. So here, we have val x equals twice 21. So x has the value 42, right? Twice of 21. We then match that. We match 42. Yeah, just a second, I'll be with you. We match 42. Unapply is applied to 42. It checks, is 42 even? Is it twice something else, in other words? Yeah, it is. Then return an option that contains that value, 42 divided by 21, to wit 21. And n is then bound to 21. And therefore, when we say print ln, it's 21. Note that this n is not, it's not a wrapped up value of sum itself. It is the value in the sum. This z divided by 2 here, which is 21. Yes, Eric?
I was just wondering, is it possible to have several unapply functions with different signatures, or?
Yes, it is.
Oh,
yes, I believe that's the case. Your choice of this unapply, for example, this might handle an int, but maybe another one that it might handle is a double or something like that. And that would be, in general, handled in different contexts. You'd be switching, you'd be matching off of different types of things, but twice would be able to handle that, okay? So you might be matching different sorts of information, and the different unapplies would handle those different cases, okay? Yeah, yeah. You'll notice that this match is not specific to twice. There's nothing in this match that says this has to be a twice or something. It's the fact that we said twice here of n, you know, that clues it in to use twice as unapply, right? These other cases might not use twice. They might use other things. So the point is, we said twice of n here. What unapply is getting called will depend on the value of x that's being matched here, right? And if x were a double, maybe you'll be looking for an unapply of double. Yeah. Pretty sure that's the case. I'll double check that. Okay, so I had mentioned last time case classes, okay? Now case classes provide a particularly neat way to support this sort of deconstruction. And so here we have a class like this, class and spec, left specification and right specification. And here, ladies and gentlemen, you can just use the name of the class to build it. Just like you know, the idea is you could sort of call it and spec, left expression, right expression. That will build one of these. You don't have to say new. Now, having done that, these are immutable. These are immutable classes. They're designed to contain these sort of things and not change. And they automatically contain a val field for each parameter, unapply method, and apply. Okay? And the unapply method will take it apart in matches. Okay? And they have some other elements. Ladies and gentlemen, we're going to see then how these could be decomposed. So given a case class like this, then you can write a case like this that will take it apart. So here, for example, we have a case class being matched. And we say, okay, is this an AND specification? If so, extract these two components, or an OR specification or a NOT specification. And this, we don't have to manually write the unapplied. That just comes from the fact that it's a case class. And you write a case class like this. You actually say, in the class, this is my class, and it has these fields in it. And it will automatically generate the unapply method needed to make this happen. Okay? So here we can handle these different possibilities in a really nice way without manually writing unapply method. It just comes right out of this thing. And so here this case class is being used to kind of bundle up this information in a way that will let us really easily match it, really easily extract it, but it doesn't have a lot of logic typically associated with it. You can extend case classes with other operators, with other methods and so on, but sometimes they're just used to sort of store this very simple sort of information. So this is the sort of code that might be used if you had a bunch of different types of specifications. Okay, so case classes factor in directly to matches in a really nice way by allowing you to match things that can be taken apart into many, many pieces if desired, and then you can use these things that have been matched over here on the right-hand side. Okay, you can use them in your expressions on the right-hand side to handle each case. Does that make sense? Case classes, very common, and I can't remember, were any of you on the team last year? Gosh, is it 2 years ago now? In 371 that was using Scala on the server side?
Eat safe.
Sorry?
Eat safe.
Eat safe, yeah. Yeah, you were on that?
Yes.
Yes, yes. There were quite a few case classes there. I don't know if you remember them. They were quite common. I think Mike Hofford had a.
He was a bit of a Scala evangelist.
Yeah, exactly. There were lots of case classes being used in this sort of way to sort of handle these different cases. And it makes for a very crisp, simple syntax. You don't want it to replace polymorphism. If there's some general thing being done in these classes that's to be done in a very regular way, then just define an overloaded method and just call it instead of doing a match and all possibilities. Matches are nice, but they are a bit fragile. If you have another class which has to be handled, they won't automatically put this in. But if you have polymorphism, every time you add a new class, you define that method, it'll automatically handle all those methods when you call a.perform task. All you know is it's an A, but secretly it could be a B, C, D, and in the future an E. And if you add an E and you add perform task to it, if you call the A perform task, it will automatically handle this case. Matches you have to extend manually. So you've got to be cautious with polymorphism. You can handle certain things better than with match, even with match expressions in Scala. Okay, that's all for today. Thank you, and I will be posting that code for aspects, and I'll be talking with the tech staff today to make sure that we can figure out why those expressions, that code wasn't working over in Sphinx. Thanks very much.